Iron did not make Iron Age Britain more violent. It just made violence more readable, because now you could look around and immediately tell who controlled the forge. Let me put a deeply held misconception on the table first. The story goes that iron replaced bronze, and humanity moved into a more advanced era. That sounds reasonable enough. But the physical evidence does not support it. Bronze did not disappear. Long after iron objects became common, bronze kept showing up in jewelry, ritual items, and fasteners. Both materials existed side by side, each dominating different contexts. Iron moved into tools and weapons. Bronze stayed in the world of symbols and display. That division alone tells you something important. The choice of material was never a purely technical question. It was a social one. So what made iron so difficult? The difficulty was not in discovering it. The difficulty was in mastering it. Iron ore is everywhere. But turning it into usable metal requires a device called a bloomery furnace, and it requires holding the temperature precisely between 1100 and 1200 degrees Celsius. Too low and the reduction is incomplete. Too high and the iron melts away entirely. Iron's melting point is 1538 degrees Celsius, far above bronze, and no technology at the time could reliably reach it. So the entire process depended not on equipment but on people. On the person standing next to the furnace, reading the fire, adjusting the airflow, judging the fuel density, and the ore grain size from experience alone. Experimental archaeology has shown repeatedly that even with the same furnace and the same raw materials, different batches can produce iron of dramatically different quality. This was not standardized production. This was craft. What came out of the furnace was a spongy lump of iron, full of impurities and voids, and it had to be reheated and hammered over and over before it became usable metal. The hammering itself was a separate skill entirely. Researchers examining cross-sections of iron objects under microscopes can read the grain structure, the distribution of pair light, and the evidence of how many times something was heated, how it was folded, and where it was welded. Among the iron objects found in Britain, one particular approach stands out: the blade made with high-carbon steel, the spine with low-carbon iron, the two welded together. Hard edge, tough back, both requirements met at once. This was not an accident. This was deliberate material design. The Smiths had no concept of carbon as we understand it, but they knew clearly that iron treated differently behaved differently, and they put different types in different places. Which raises the obvious question: who got to possess this knowledge? Smelting and forging could only be learned through doing. There were no written records, no manuals, only the judgment that accumulated after years of standing next to a furnace. Knowledge moved only between people who had direct contact with each other. That, naturally, produced a monopoly. Not a deliberately engineered one, but a structural one. You had to learn from someone who already knew, and people who already knew did not take on students casually. The group that controlled smelting knowledge held more than a trade skill. They held a form of social capital that others could not easily replicate. Now look at charcoal. Smelting 1 kilogram of iron consumed several times that weight in charcoal, sometimes up to 10 times. Where did the charcoal come from? From burning woodland. But not burning it randomly. Managing it systematically. Pollen analysis and charcoal identification show that in areas where iron production was concentrated, the vegetation changed in recognizable ways. Fast-growing species like birch and alder increased in proportion. That pattern matches what is called coppicing, the practice of cutting trees periodically to encourage new growth from the stumps, then cutting again after several years, cycling through the same land continuously. The forest was no longer just part of the natural environment. It was a managed fuel system. At some sites, calculating backward from the total volume of slag to estimate how much charcoal would have been needed produces a figure that exceeds what the surrounding woodland could reasonably have supplied. That means charcoal had to come from further away, and bringing it from further away means someone was organizing that process. Iron production was therefore never a solitary activity. It was a chain: mining, charcoal burning, smelting, forging, distribution. Each stage had its own technical requirements and resource demands, and they were offset from each other in time. Charcoal had to be prepared months in advance. Ore extraction was constrained by season. Forging required permanent facilities. Keeping the chain running required coordination. And coordination is power. The archaeological record contains a telling detail here. At several sites, smelting slag and forging waste appear at separate locations, with distance between them. Smelting and forging were happening in different places, which means iron was being moved in semi-finished form. Semi-finished iron is easier to transport and can be worked by smiths operating at different levels of specialization. This is functionally close to raw material trade. Who was doing the moving? Who was deciding where it went? The answers to those questions are the answers to what power actually looked like. Now come back to violence. Bronze weapons depended on tin and copper, and tin was not evenly distributed. Britain had very little of it. Bronze weapon production was therefore structurally dependent on long-distance supply, and output was constrained by what could be sourced from outside. Iron ore was widespread, with usable deposits across Britain, and in theory anyone could get hold of the raw material. But between having the raw material and producing a functional weapon stood three major obstacles: smelting technology, forging skill, and charcoal supply. The wider distribution of iron ore did not translate into any real democratization of weapon producing. The people who could produce good weapons were still the people who controlled the production chain. Metallographic analysis encodes that inequality directly into the objects themselves. Iron sword blades typically used high-carbon steel at the edge, with low-carbon iron retained at the spine for toughness. Spearheads were generally worked to a medium carbon structure, balancing penetration with resistance to fracture. These choices required the smith to understand how different parts of a weapon were stressed in use, and to process the metal accordingly at each stage. Agricultural tools and everyday cutting implements from the same period are almost universally simple low-carbon structures, with noticeably lower precision throughout. The gap in technical investment is written directly into the grain structure visible under a microscope. Use-wear analysis adds another dimension. Some excavated iron swords carry the marks of actual combat use, irregular edge folding, and deep microchipping consistent with heavy impact. Others show almost no wear at all, yet their metallurgical quality is higher. The ones with no wear were clearly not made for fighting. They were made for display. Weapons served two functions simultaneously, as instruments of actual force, and as media of social identity. The difference in manufacturing standards between these two categories reflects two entirely distinct logics of use. So how violent was Iron Age Britain actually? The bones answer that. Systematic re-examination of skeletal remains from this period shows that trauma rates were considerably lower than some theoretical models would predict, and varied substantially across regions and time periods. The widespread presence of iron weapons did not translate into an overall increase in violence. Iron provided the material conditions for coercive capacity, but between that capacity and how it was actually mobilized sat a layer entirely filled by social relations. Who could call on violence, under what circumstances, against whom? Those were questions determined by social structure, not by the material properties of iron. What iron changed was rendering that structure visible. Settlement archaeology shows that iron objects were not evenly distributed across different residential units. Some had higher densities, greater variety of object types, and higher quality smelting remains nearby. Others had sparse, low-quality iron, or none at all. That spatial distribution is a direct material record of inequality in everyday conditions. Burial evidence confirms the same picture. Graves containing iron swords and high-quality blades consistently show greater overall investment across all other burial dimensions as well. The type and quality of iron objects present at the moment of death continued to mark the social position the individual held during life. There is also the question of repair. Iron can be fixed. Reheat it, hammer it back, grind the edge, and it works again. Many excavated iron objects carry the marks of multiple repairs and repeated reworking, evidence of long use and continuous maintenance. But repair requires forging skill. When an iron object broke, the owner had to find a smith. That recurring need for repair services could become the basis for a long-term relationship between smith and user. Not a single exchange, but a sustained dependency. The smith needed users to bring work and payment. The user needed the smith to keep tools functional. That mutual dependency is one of the basic materials from which social networks are constructed. Put all of this together and what emerges is a map of Iron Age British social structure. The coordinates on that map are not tribal boundaries or territorial claims. They are who controls the ore source, who manages the woodland,